All right, guys. So, as promised, I'm going to do a few more practice problems for you here, covering stuff from 9.1 through 9.6, broadly speaking. Um, so, mostly just looking at series and their convergence, um, and looking at some special problems. Right. So, let's look at this one here. Looking at the sum as from n equals 1 to infinity. We've got an alternating component here, and then this guy. Right? So we might take a look at this and think various things, but I think the most immediate or useful thing to notice is that we've got especially if we're looking at absolute convergence, we've got a fixed term in the numerator and then something of square root in order in the denominator. So this looks a lot like an alternating p series with p equal to 1/2, which means we'd expect some sort of conditional convergence. So let's see what happens with this. So first we have to look at absolute convergence, right? So we'll look at this. The alternating component will go away, and we'll just be left with this. Over 1. And it's our expectation that this would diverge, right? Because we have roughly speaking, if we squint our eyes, a square root of n power in the denominator. So this looks like a p series, a divergent p series, but we need to show that, right? So there's probably any number of ways to do that. I think just to spice things up, I'm going to do a look at a limit comparison test. So, right, limit comparison. What are we going to compare it to? We're going to compare it to this guy, whose divergence we know well as a p-series. So let's see what happens. So we're looking at the limit as n goes to infinity of 1 over all this madness divided by this guy, right? So we're looking to use the LCT here, right? So it's not the ratio test, it's not the root test, it's a limit comparison test. So we're making a ratio out of two sequences. And you got to remember how the limit comparison works. Depending on what value this goes to, if it converges to something less than 1 all the way down to 0, then if we're comparing it to something convergent, then we'll get convergence. If we're comparing it to something divergent, we'll get divergence. If it converges to something greater than 1 or diverges to infinity, then if we're comparing it to a divergent series, then it implies divergence, right? And if it converges to 1, then it's inconclusive. Okay. So what to do? Let's see. Let's just do some algebra here. Bring up the root n. Just looks like this. Right? And then what? What are we going to do? We're going to have to do some trickery with this because we don't see something whose limit we can compute right away. If we plug in infinity, then we're going to get infinity over 0, which is not an indeterminate form that we know how to deal with. So going the L'Hopital's route doesn't seem viable. But what we could do is we could factor out a square root of n from the denominator. And if I do that, then what do I have left here? I have root n plus 100 over root n all minus 1. And so this will simplify. These guys will cancel out. And we'll be left with 1 over this stuff. And we could just write this as one big radical if we want. Okay. So now what? Well, now we can actually assess the limit. So if we look at the limit in the denominator, this term that depends on n, we have the same power of n in the top and the bottom. So this whole thing is going to converge to 1. And then we'll have a 1 minus 1, which will give us a 0. And since we have a fixed number, 1 in the top, this will equal 1 over 0, which is infinity. So we actually learned something even more important here, which is, ultimately, what do we learn? We learned that the absolute series is divergent, right? We learned that this guy is divergent by the limit comparison test. And go back and look at the definition of the limit comparison test. It's a little involved, but because we were comparing it to a divergent series, and we ended up with a divergent sequence, the limit comparison test tells us that that should imply that we have divergence. Yeah. But that only applies to the absolute value of the series. So all that tells us is that it's not absolutely convergent. So we always have to go back and check to see if we have conditional convergence. So what do we need there? We need that this thing is always positive, right? So our checklist is the sequence, this guy, which I'm going to call AN. Is it positive? That's checked. Is it non-increasing? That would be the next thing we need to check. And this thing in the bottom, right, if you look at it, they're pretty much the same function, just one has a 100-unit head start. So you're taking the difference of two things. They are gradually getting closer together, which means that the bottom is getting smaller and smaller, relatively speaking. The difference of the two things is getting smaller, which means the whole thing is getting bigger. So what does that tell us? Does that tell us we have something that's non-increasing or not? Well, we can always just try to see. So we need to check what happens if we plug in an n plus 1 into this guy. And we're going to compare that to to the previous term, right? We need it to be non-increasing. So as we look at the successive terms, they should be getting smaller. So we may fail here, but we've got to take a look. So we don't know if this is true. We're checking it. So that would imply that root of n plus 100 minus root n is less than or equal to the square root of n plus 101 minus root of n plus 1. So what could we say here? Well, we know that these terms are definitely, this term is definitely smaller than this term incrementally. But we have a subtraction here, and subtraction makes things go haywire when we're doing these comparisons. So we have to do it pretty carefully. How might we do that? Well, if in doubt, you could always start plugging in values if it doesn't appear clear to you. But it's my expectation here that we're going to end up with something that doesn't work. So how could we show that? Just trying to reach for it here. If I move things around, then I could write it like this. And this thing might make it a little bit easier to compare. So what we know is that, these two things differ by 1, but because this one has 100 units in addition to it, these two terms are actually closer together than these two terms, right? So let me get out a calculator so you can see what I'm saying. So just, notice that these two things they only differ by 1 point, right? One has n plus 1, one is just n. And the same thing is true here, except that you have 100 extra terms. So just for instance, if I look at the square root, I'm doing bad math here. Square root of 3 minus the square root of 2. What is that going to give us? That's 0.318, right? But if I had done the square root of, in this case, I plugged in n equals 2, so we would have 103 minus the square root of 102. What do we get? We get something that's much smaller. You see that? So even though they only differ by 1 point, this is kind of the how calculus works. They're getting closer and closer together as you move further down the sequence. So the difference of these two things is much smaller than the difference of these two things. And so if we come back here, we see that we have a statement that doesn't make any sense. Right? These two things, the difference here is bigger than the difference here. So this fails. So this implies that we also don't have conditional convergence. So if you like, we could say this thing is absolutely divergent, right? It is as divergent as you get. So it fails the alternating series test. So this is just plain old divergent. Took a little bit of work to get there, but some careful analysis down here showed that these two things, this thing was not non-increasing. So there you go. That's the first problem. We've just got a divergent series. All right. Let's look at another one. Oh, how about this one? We're looking at the series n equals 1 to infinity log base n of n factorial over n cubed, right? So what is our expectation? This is a hard one to look at and think about because we have a logarithm, which we know grows slow, but we're plugging in something into it that's growing really, really fast. And in addition to that, this logarithm has a changing base. The base is getting bigger and bigger and bigger. So this is a complicated thing to think about, and it's hard to compare it between the numerator and cube and the denominator. So we may just have to get into the weeds with it and hack at it and see what happens. But before I do that, I need to plug in my phone because it's about to die. So bear with me. All right, I'm back. Phone is plugged in. Should be good to go. So we were looking at this thing and we're like, oh, I don't really know what's going on with this. It could be convergent, it could be divergent. What to do, right? So let's just start taking a swing at it. Now, if we want to prove convergence, as I said, the technique I reach for the most is the direct comparison test. The other tests are totally viable, but sometimes they just have special places where they're better used, right? So we know that the ratio test is great for factorials, but the factorial here is trapped inside of a logarithm. So what can I do with that, right? Root test is great for powers of n, but I don't have any powers of n here. So direct comparison is just my first thing to think. So we're going to write down the sequence. And if I want to prove convergence, which looking at this thing, it's hard to say one way or the other which way it should go. But if I wanted to prove convergence, I would need to show that the sequence is less than something else. And maybe that thing would ultimately be a convergent series, right? Its corresponding series. So here's the thing to use here. Just like with the natural log, there's a handy fact when it comes to factorials. So this is one you can take to the bank. N factorial is strictly less than n to the n for all n. So there's not much that outgrows the factorial, but n to the power of n is it. So as far as we're concerned in this class, this is the fastest growing function or sequence that we know. It's n to the n. So n factorial, in fact, is smaller than that. So if I use that fact here, maybe something will happen. So I know that I'm looking at the numerator, right? When I have the numerator, then I can use the inequality directly. And I'm allowed to do this, to apply this inequality here, because the logarithm is, say it with me, monotonic. So I know that, if it's true for n factorial, it's true for log of n factorial, even if the base of the log is changing. So you can't just do this for any old function, right? You've got to be careful. Some functions that are not monotonic would fail this. So the log base n is good. And we take a little look at this side and we get some magic happening because we have a log base n, and here we have an exponential with a base of n. So this will simplify to just n, right? That power of n will come down to the front using the log rules, and we'll just be left with an n. And that's over n cubed, which simplifies to 1 over n squared. So we've shown that this sequence is always less than 1 over n squared, and we know that the corresponding series of 1 over n squared is convergent by the p-series test. Therefore, that implies our guy is convergent by direct comparison test. That's a nifty little one. It falls together pretty quickly as long as you have this fact at your fingertips. So that is one that it's worth holding on to. If you see an n factorial, it may come in handy. All right, let's do some more. So here we're looking at the series n equals 1 to infinity, -1 to the n times n squared plus 1, all divided by 2n squared plus n minus 1. Right. So, maybe you're getting better at this by now. You're starting to look at these things and start seeing the forest for the trees or the trees for the forest or whatever the case may be. So really quickly, we can look at if we take off the absolute value, if we take off the -1 to the n, the alternating part, then we're looking at the limit as n goes to infinity of n squared plus 1 over 2n squared plus n minus 1. So this is a rational polynomial where the numerator and denominator are of the same degree. So we know precisely what this converges to. Converges to the ratio of the leading coefficients. So that's 1 over 2, which indeed is not 0. So that implies that this series is divergent, and that's by the VIT, right? Our very important theorem, which says that the sequence that corresponds to the series must go to 0 if our series is to be convergent. So this one fails. It's not going to be absolutely convergent. It's not going to be conditionally convergent. It's just plain old divergence. All right, let's look at some more. So actually, yeah, this one's a little bit different. One thing I haven't done a whole lot with you guys, which is worth seeing, is translating a series as its. Hold on, guys, 1 second. false alarm. I thought I heard someone knocking. Right. So one thing we haven't talked about a whole lot is um, given a sequence sort of, or sorry, a series in expanded form, how do you translate it into the nice compact series notation that you're getting used to now? So, excuse me, we'll get a little practice of that here. So let's just say you're handed this series, 1 minus 1 over root 3 squared plus 1 over root 3 to the 4th minus dot, dot, dot. Okay. So you need to translate this into a series. So how do you do that? Well, when you're doing that translation, you want to look for patterns, obviously. And one of the obvious patterns here is that we have something that's alternating. So we're starting off with positive and negative and positive and negative. So that means we're going to have an alternating component. That would just be a -1 to the n. And since we want to start off with a positive, we want to make sure that our series starts off at 0. All right, so we have an alternating component. And then the other component you might surmise is something to do with 1 over the square root of 3. But if you're paying close attention, you notice that the powers of the square root 1 over square root of 3 are all even powers. We have no odd powers here. So if I want to represent that, it's going to be 1 over root 3 to the 2 times n. So convince yourself that this does work. If I plug in 0, then I get a positive 1 here, and then I get a 0 power here, so that's just 1, so that works. Plug in 1, that becomes negative, and this becomes 1 over root 3 to the 2nd power, so on and so forth. So this totally works, and looks cool, looks vaguely like a geometric series, except that we're only looking at the even powers. So that's not our usual definition of a geometric series. How might we manipulate it to look like a standard geometric? Well, I could just square the inside and put it in the power, right? So basically I'm distributing the 2 to both the parts, and that turns this into a 1 over 3 instead of a 1 over root 3. And now the n is integer powers. So interestingly, it looks like this thing is equivalent to the alternating geometric series, -1 to the n times 1/3 to the n. Right, so alternating geometrics, we know that that's absolutely convergent. It's more than just convergent, it's absolutely convergent. Since this guy is a geometric series with r equal to 1/3, which is indeed less than 1. So thought that one was good just because it made you translate the series into some compact form and then do a little bit of a tweak so that you get an actual alternating geometric series there, which we know how to work with, right? So do expect that you will have to sometimes tweak these things in order to make them look the way that you want them to. And it's good practice, for future classes. Like I mentioned, in ordinary differential equations, if your professor is thorough, they will teach you the so-called power series technique. And we'll be learning all about power series and then tomorrow, basically. I'll be posting a lecture about it anyways. But when you're doing these power series techniques for solving differential equations, they're super versatile. So you can, if there is a solution, the power series technique will yield a solution. It may not yield one that converges to something nice and sweet. Like I mentioned in class, it might not converge to something like a sine or a cosine or e to the something or whatever, but it will be a convergent power series. And when you're working with those power series in ODE, you have to do all types of manipulations with them in order to make them work. So getting some practice here is useful. Right. Okay. So just a couple more. Just a couple more. This might not be a full 50-minute lecture, but I have done quite a bit of problems with you guys, so I'm sure you won't mind a little bit shorter lecture if it ends up being shorter. All right, let's look at this guy. So we're looking at the sum, n will equal 1 to infinity, and it'll have an alternating component, then an inverse tangent of n all over n squared plus 1. Okay, so what do we expect? What do we expect? Well, just trying to get a feel for this thing. The inverse tangent is actually a bounded function. So other inverse trig functions are not necessarily bounded. Well, I'll take that back. They are all bounded, I believe, but don't quote me on that. But in particular, tan inverse is bounded. So since we have something bounded in the numerator and we have an n squared term in the denominator, this maybe will look like a convergent p-series in the end, an alternating one, but nevertheless. So I'm going to expect convergence. We just need to show it. So this will ultimately amount to a direct comparison. We'll look at this guy. And as I said, tan inverse is bounded, right? So we know that this is less than or equal to pi over 2 over n squared plus 1. And remember what the inverse tangent function looks like if that confuses you. It's a sort of S curve like this, and it has asymptotes. And those asymptotes are at pi over 2 and negative pi over 2, respectively. So as n grows really, really big, this thing converges to pi over 2. So this is a good statement. And so, this guy looks like a convergent p-series. The pi over 2 doesn't matter. So this one falls out pretty quickly. We don't have to do a whole lot of work with it. I can say since pi over 2 times the sum over 1 over n squared is convergent by the power series test, implies that power series is not only convergent, right, but absolutely convergent. So maybe I've been a little loosey-goosey about this, but how do we get to this step here? We're always sort of checking. We're checking absolute convergence here, and that's always sort of our first step. technically I'd say your first step is always does the sequence, if you ignore the series part, does that go to zero? The VIT is sort of your first step. It's clear here because tan inverse is bounded and we have something that's growing in the denominator, this thing's going to go to zero. So the VIT is satisfied. So then we start checking absolute convergence. So that's important to remember where you're situated, because we're not saying that we have a convergence series. We're saying something stronger. We're saying that this is absolutely convergent, and we're doing that using the direct comparison test yet again. So, this one is a quick and sweet little problem. As long as you remember what you need to remember about tan inverse, it falls together pretty quickly. It's just a little comparison. It's very nice. All right, let's see, maybe one more. I think I had one more on here. That was decent. Yeah. Right. Okay. So last one, and then I'll leave it alone. So we're looking at the series n from 1 to infinity of 1 over 3n minus 2 to the n plus 1 half. Okay. So this one's funky because this is not a p-series, right? It's not a p-series. So what do we do with it? Well, it definitely seems like it's going to be convergent because, ultimately, if we squint our eyes, what does this thing look like? It looks like this, more or less. And we know that this thing is the fastest growing function there is, so this thing is going to converge really quickly. We just have to show it. So we're definitely expecting convergence. We just need to show it somehow. Okay, well, how do we do that? Well, yet again, like I said, my first place, the first one I reach for quite often is the direct comparison test. So if I do that with this one, then I've got a power of n plus 1/2 in the denominator. So if I compare it to something whose power in the denominator is smaller, then I am dividing it by, I'm dividing 1 by a smaller number, right? Power n plus 1, n plus 1/2 is less than n. So 3 to the, n plus 1/2 is greater than n. So if we have that in the denominator, then we'll get something that's less. And so that's a little bit easier to work with. But we don't know anything about this series here. So remember, when we're doing direct comparison, we need to trap our sequence above something, some other sequence whose series we know is convergent, but we don't know that this series is convergent. So now we need to look at yet another series. Right, this is the one we want to know about, but now we're looking at this one. Why? Because we're able to compare it to this one. So we're kind of saying, like, we're starting from scratch. What if this was the problem, right? Ignore all the stuff that came ahead of it. How would we assess the convergence or divergence of this? Well, Yet again, we expect convergence because it's kind of like n to the n in the denominator. But how do we do that? Well, we've got an nth power here, and we know there's one test that's particularly good at that. So we'll look at the root test. We're looking at the nth root of the absolute value of our guy here. And in particular, we're looking at the limit as n goes to infinity. Okay. So we'll get some simplification here, right? We're going to nth root. So absolute values go away. We take the nth root and we just end up with 1 over 3n minus 2. And that's it. Well, that limit is easy. That's just going to go to 0. Okay. So we're using a root test, and we got it converged to 0. The series converged to 0. So we got to remember how the root test works. So since our guy converged to 0, which is less than 1, and the, what am I trying to say? Right, that's it. So there's no and. So since it converged to 0, I was thinking of a limit comparison test. Since it converges to 0, which is less than 1, that implies convergence by the root test. You definitely want to look those guys over, but it's more than that. It implies absolute convergence, right? That's what this was all about. So we got to chain it all together. So we used the root test to assess the convergence of this series. Well, this isn't the series that we want to know about. We want to know about this one. So now we know that up here, the series that we're comparing to is absolutely convergent. So that implies that our series is convergent, absolutely convergent, sure, but convergent anyways, is convergent, and we get that by direct comparison. So yeah, again, a sweet little problem, multiple layers. You're having to do a comparison and a root test all in one problem. So I particularly enjoy that. I like them when you're putting multiple theories together. Well, anyways, that is all that I really wanted to go over. I'm not quite sure what I clocked in at, but it's not nothing. It's at least a majority of a typical lecture. So you guys will have a quiz tomorrow on this stuff. I'll make sure that this is posted for you guys to go over. And I'll also be posting a lecture tomorrow covering 9.7. So we're going to start getting into power series tomorrow. And then we'll meet in person for real on Tuesday. All right, guys, have a good one.